Good morning to all of you. Good morning to all of you. This is lecture number 5. In this lecture, we will discuss about simple stress and simple strain, and what is the meaning of principal stresses and principal strain in case of complex geometry. Introduction. In the previous chapter, we have covered thermal stresses and simple stress and strain, but in today we will discuss about what is the role of principal stresses in the strength of material. The concept and definition of stress and strain, types of stresses and types of strain, that is tensile, compressive, shear and volumetric strain, etc., are discussed in previous slides. These stresses were acting in a plane which was at a right angle to the line of action of the force. In many engineering problems, both direct, that is tensile or compressive stress, and shear stress are acting on the same at the some time. In such situation, the resultant stress across any section will be neither normally nor tangentially to the plane. In this chapter, in this lecture, the stresses acting on an inclined plane will be discussed. So, first of all, what is principal plane and principal stresses? The principal plane which have no shear stress are known as principal plane. Hence, the principal planes are the plane of zero shear stresses. These planes carry only normal stresses. The normal stresses acting on a principal plane are known as principal stresses. Next is method for determining stresses on oblique sections. The stresses on oblique sections are determined by the following methods: graphical method, that is Mohr circles, and analytical method. So, analytical method for determining stress on oblique section. The following two cases will be considered. The first one is the member subjected to direct stresses in one plane. The second one is the member is subjected to like direct stresses in two mutual perpendicular directions. So, first case is a member subjected to a direct stresses in a plane. So, the figure 3.1 shows the direct stresses on a plane. Suppose the inclined plane is EFG, which is inclined at an angle theta with a plane of EF. So, the area of EF is equal to EF multiplied by 1, that is 8. The stress on the section EF is given by sigma is equal to force divided by area of EF is equal to P upon A. The stress on the section EF is entirely normal stresses. There is no shear stresses or tangential stresses on the sections EF. Now consider section FG at an angle theta with the normal cross section EF as shown in the figure 3.1a. The area of FG is equal to FG multiplied by 1, or EF multiplied by 1 divided by cos theta, or it is equal to A upon cos theta, because A is equal to EF multiplied by 1. So, stress on the section FG is equal to force upon area of section FG. So, P upon A upon cos theta, or it may be P upon A cos theta, or sigma cos theta, because P upon A is equal to stress is sigma. This stress on the section FG is parallel to the axis of the member, that is, this stress is along x-axis. This stress may be resolved in two components. One component will be normal to the section FG, whereas the second component will be along the section FG, that is tangentially to the section FG. The normal stresses on tangential stresses on the section FG are obtained as given below. Normal stresses and tangential stresses across the FG are obtained as sigma n, that is normal stresses is equal to force normal to section FG whole divided by area of section FG, or mathematically Pn upon A upon cos theta, or P cos theta divided by A upon cos theta. By solving this, P upon A cos square theta or sigma cos square theta, because P upon A is equal to stress, which is shown in figure 3.2. The tangential stress, that is shear stress, that is sigma T, is equal to tangential force across the section FG divided by area of section FG. Or by solving this, the last expression of tangential stresses, that is shear stresses, is equal to sigma by 2 sin 2 theta. Here. Now we will discuss one problem which is based on the previous discussion. A rectangular bar of cross section area of 1100 mm square is subjected to a tensile load of P as shown in figure 3.3. The permissible normal and shear stresses on the oblique plane BC are given as 7 Newton per millimeter square and 3.5 Newton per millimeter square respectively. Direction: the safe value of P. Determine the safe value of applied load P. So the given values: A is equal to 1100 millimeter square. Normal stresses, that is sigma n, is equal to 7 Newton per millimeter square. Shear stresses is equal to sigma T, and it is equal to 3.5 Newton per millimeter square. And the angle of oblique plane with the axis of bar, that is 60 degree. Therefore, angle of oblique plane BC with respect to normal cross section of the bar, that is theta, is equal to 90 minus 60, or it is equal to 30 degree. Let P is equal to safe value of the axial pull, sigma is equal to safe stresses in the member. But we know that the normal stresses on an oblique plane, that is sigma n, is equal to sigma cos square theta. Putting all these values, 7 is equal to sigma cos square 30, and sigma is equal to 9.334 Newton per millimeter square. As similarly, we know that the tangential stresses, that is sigma T on an inclined plane, that is shear stresses, is equal to sigma by 2 sin 2 theta. Here theta is equal to angle of inclination. So sigma 2 is equal to 3.5, this is given, is equal to sigma by 2 sin 2 into 30 degree. By solving this, sigma is equal to 8.083 Newton per millimeter square. The safe stresses in the list of 2, that is 8.083 Newton per millimeter square. The safe value of axial pull is equal to safe area multiplied by safe stresses multiplied by area of the cross section, that is 8.083 multiplied by 1100, and it is equal to 88.913 km. Member subjected to two mutual perpendicular stresses. Figure 3.4 shows a rectangular bar ABCD of uniform cross section A and a uniform thickness. The bar is subjected to two direct tensile stresses or two principal tensile stresses as shown in the figure 3.4a. Figure 3.4a shows sigma 1. This one is sigma 1. This is sigma 1. This is sigma 2. This is sigma 2. Sigma 1, the stress is acting in x direction, and sigma 2 stress is acting in y directions. Let FC be the oblique section on which stress are to be calculated. This can be done by converting the stresses sigma 1 and sigma 2 into equivalent forces. Then these forces will be resolved along with the inclined plane FC and perpendicular to FC. Consider the forces along on the FBC, that is FBC. Let theta is equal to angle made by the oblique section FC with normal cross section BC. Sigma 1 is equal to major tensile stresses on the face AB and BC. Sigma 2 is equal to minor stresses on the face AB and CD. E1 is equal to tensile stresses force on the face BC. E2 is equal to tensile force on the face FB. Therefore, the tensile force on the face BC is equal to E1, that is equal to sigma 1 multiplied by area of face BC, and it is equal to sigma 1 multiplied by BC. And the tensile force on the face BC FB is equal to stress 1 FB multiplied by area of FB, that is sigma 2 multiplied by 2 multiplied by the tensile force P1 and P2 are along the oblique section FC. The force P1 and P2 acting in axial direction only. So Pn is equal to total force normal to the section Fc, which is equal to component of force P1 normal to the section Fc plus component of P2 normal force on section Fc. On solving this equation, the final expression of the normal stress is that is sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta. Today in this lecture, we have covered the principal stresses both a single plane and two mutually perpendicular plane. In next lecture, we will discuss about the three-dimensional stress system.